Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tare, and this is my continuing feature on the Math Lovers book, three-volume series I wrote from 2019 to 2022. It's available on Amazon, both in Kindle and in paperback, in case you're interested in purchasing any one of these volumes or the whole set. Anyway, I just started a new chapter yesterday. It's on logic, and this is just my second lesson in this chapter, and I'm starting a new section now. Yesterday, I talked about Aristotelian syllogisms, which is kind of the ancient way to do logic. It was the way that Aristotle first taught logic in terms of these 24 syllogisms, which are always true, valid arguments. But it really didn't get into much math. To really make the logic into a branch of mathematics, this didn't come until the 19th century. And the pioneer was a very famous logician named George Boole. You're probably familiar with him. He was responsible for Boolean algebra, which is just another name for what's called propositional logic. Sometimes people call it classical logic. But anyway, let's begin. And this is just going to be an overview. This is going to be a pretty brief video today, but I'm just going to give you a very brief overview of propositional logic, also known as Boolean algebra, and what it's about. And it's a very powerful tool, I think, because what it does is, logic's all about making valid arguments, right? And, when we hear the word argument, sometimes we think of fighting. It's not very popular. People, when you say someone argues too much, it's usually an insult. You're saying that they're hard to get along with, they're fighting verbally, they're always attacking you. They're very over opinionated. That's kind of the reputation that people have who argue all the time, right? And I have to confess that I tend to argue a fair amount myself. I always have, which may be part of the reason why a lot of people have avoided me for a big part of my life. But, but argument, and at least in terms of mathematics, that's not what argument means at all. An argument is it's a set of just statements. It's really just a way of going from A to B logically. So you start with a set of premises, you start with assumptions, facts that you can pretty much agree, or pretty much everybody can agree are all true, and then you apply the rules of logic, which I'm going to get into here, and then you arrive at a conclusion. So it's just a logical means. It's kind of a mathematical recipe for arriving at a conclusion from a set of premises. I think it's a very powerful area of math. And by the way, all math is based on logic. Logic is just a way of proving things. And in math, you really do have to prove everything. And a lot of people hate proofs, but that's what mathematicians do. You've probably done a lot of proofs without even realizing it. Math is all about proofs, so I can't overemphasize the importance of logic in math. It's kind of the backbone of math. Without logic, math wouldn't even exist. But anyway, so I'm just going to talk about, when you're trying to make an argument, you start with a set of sentences, your propositions, and there's different types of sentences or statements. There's statements that are called atomic, and those are statements that can't be broken down any further. You can think of them kind of like elements or like prime numbers. I'll give you a few examples. I give some in my book, like 2 plus 2 equals 4. That's an atomic statement. It's a single fact, and it happens to be true. They don't have to be true, but this one's true. Or the sky is blue. That's another atomic statement. But then there's more compound statements. Like you can say the sky is blue and 2 plus 2 is 4. That's a compound statement because it consists of the conjunction of two atomic statements. And that is actually the example I give in this book. You can assign letters to atomic statements. Remember, we're doing math here. So in math, we like to use symbols like we do in algebra for unknown quantities. We can also use symbols for atomic statements. So we can call the statement, the sky is blue. In my book, I give that the letter capital S. And then our second part of our compound statement, 2 plus 2 equals 4, we can call that U. So the compound statement, the sky is blue, and 2 plus 2 is 4, we write as S with a wedge pointing up. That's a logical symbol for and. And is what's known as a conjunction. So we write S and U. S upper wedge U represents a compound statement. The sky is blue and 2 plus 2 equals 4. But there's other conjunctions besides and. There's also or. Or just looks like the upside down and. So we write or as a V. I guess an easy way to remember this, and begins with the letter A. And the upper wedge looks like an A, except for it doesn't have a line going across. Or looks like a V. Is there an easy way to remember that? It's just the opposite of and. And these are very closely related. Another easy way to remember these is that these logical connectives, as they're also called, conjunctions or logical connectives, they're very closely related to union and intersection. Or is like the union, and is like the intersection. I'll get into that more in more detail on further lessons. I'm going to give a lot of lessons on Boolean algebra, but just for now, keep that in mind. And is like the intersection, or is like the union. And means is sort of exclusive, and or is inclusive. So you could say the sky is blue and 2 plus 2 is 4. And that's only true if both of those atomic statements are true. But you can say the sky is blue or 2 plus 2 is 4. That's true if either of them is true. They don't have to both be true, but either one or the other or both. And it's also true, for instance, we could say the sky is blue or 2 plus 2 is 3. Obviously, 2 plus 2 is 3 is false. But the conjunction of the disjunction, and is also known as conjunction, and or is known as disjunction. The disjunction of two atomic statements is true if just one, at least one of them is true. But the conjunction is that's exclusive. That's true only if they're both true. So that's and or. The other one that's commonly used is not. That's negation. So the not S would be the sky is not blue. And, since the sky is blue, that's true. The sky is not blue, that we would write that as not S with a kind of funny looking symbol. It looks a little like a minus sign, but it's got a little vertical shelf on the right to distinguish it from a negative sign. Sometimes people do use a minus sign. I prefer this funny looking symbol. It's a standard one used in logic. So we call that not S. So if S is true, then not S is false, and vice versa. And so those are kind of the basic logical operations, and or and not. You can come up with other ones, and there are a lot of other ones that are commonly used. I guess I should have switched to the next slide here. There's also this arrow symbol, which is implication, if then. So we could say if I'm trying to give an example. If if it rains today, I won't go outside. So it rains today. That's an atomic statement. I won't go outside is another atomic statement. So we can write, I guess say it rains today, I could call that R, and then I'll go outside, I could write as O. So I write R arrow O. That means if R, then O. And there's also double implication. That would be there's different ways people write this. I think in my book I write it as the 3 lines. This is also the same symbol used for congruence or equivalence. I think you've seen that in that context. So I could say I won't go outside if and only if it rains today. That would be a double implication. That means that implies in both directions. And then there's also exclusive OR, which is usually written as a plus sign with a circle around it. That means either A or B, but not both. And then sometimes that's how people think of OR. I mean, the way OR is used, the V symbol, it means either A or B or possibly both. But if you want it to be exclusive, then you have to exclude the possibility that it's both. So anyway, those are a couple other logical connectives that are commonly used. But you can build everything up from and, or, and not. Actually, it turns out you can build them up from just and not, or just or and not. And there are even weirder ones like NAND that people have come up with. I don't discuss this in my book, but it turns out NAND, not and, that is actually logically complete. You can express any statement in Boolean algebra just using the NAND operation, but then you get some really ugly expressions involving it. I don't really like NAND. I guess a lot of computer scientists don't do. There's also NOR, which is not or. That also turns out to be logically complete. But anyway, I'm kind of jumping the gun here. I'm gonna go into this in much more detail in future lessons. Like I said, we're gonna actually do some math starting tomorrow, starting my next lesson. I'm gonna introduce truth tables, which is a very convenient way for expressing, the truth or falsity of different compound expressions in terms of their atoms, their atomic statements that they're built up from. And we'll start that next time. But anyway, that concludes my video for today. Introduction to propositional logic or Boolean algebra. So thank you for watching. Long live math, and I'll see you guys next time. Bye.